Okay, so last time we talked about Dutch-Jones algorithm, and we're gonna briefly review the last part of Dutch-Jones, and then we'll move on to the new algorithms. So let me draw Dutch-Jones algorithm first. So basically, it's about a function that sends n-bit string to 1-bit string, and we initialize the input register and output register at 0 and apply Hadamard, and then Oracle, and another Hadamard, and then we take a measurement. So at this moment, you don't have to put the Hadamard on output register because it doesn't do anything here. But if you want to, you can put Hadamard here too. But anyway, it only depends. The result is only depend on the read off of the input register. So from this from this observation, we can infer the characteristic of the function. So whether it's constant or balanced. So we talked about the last stage, so the stage 3, and the quantum state is given by 1 over 2 to the n over 2. So let me assume that we had a stage 2 and then apply Hadamard. So it will become x from 0 to 2 to the n minus 1 and apply Hadamard on I think I should take minus 1 out, minus 1, f of x out, and apply Hadamard on the quantum state x on the input register, and minus cat. All right, so again, I think this will happen, appears many places from now on. So let me rewrite again. So when you apply Hadamard gate on n qubits in an n qubit state with quantum state as x, so which means that we have x represented as a binary representation of xn minus 1 up to x0. So this means I apply Hadamard on xn minus 1 for n minus 1 qubit, the indexed as n minus 1, and then this is what I'm doing here. And depending on whether xi's are 0 and 1, it becomes plus cat or minus cat. But let's say we can always write it as a tensor product. So it's only matter of sign of the 1 cat in the minus 1 cat or plus 1 cat. So so that's 1 over square root. So this is the quantum state of this 1 qubit state. And then this one. So when you do this, you basically get a superposed state of 2 to the n number of quantum state, base states. But the signs are different now. So sign depends on how many 1 cat you choose at each place of your binary digits. So the number of minus 1 you choose from, and also not only that you choose 1, it's when you have a minus 1 sign at that place. So the number of the minus 1s you choose for each number, let's say y, depends on what is the digits of y at the ith place. So yn minus 1, xn minus 1. So if the yn minus 1 is 1 and xn minus 1 is also 1, then you choose -1 at that place. So that's where you get it. And you do it up to 0's place, so y0, x0. And then once you do that, you just collect all the numbers of 0's and 1's whose ith coordinate, which are ith digits of the number y. So we simplify this notation as 2 to the n over 2, y from 0 to 2 to the n minus 1, minus 1, x dot y, y. Okay. All right, so therefore, this psi 3 is now becoming n over 2 x and minus 1 f of x and y minus 1 x times y, y, tensor product minus ket. Okay, so let's write it as the sigma of y, so, and make everything else to be the coefficient of y ket. I forgot to put the n over 2 square, so so it becomes 2 to the n sigma y. So y and x also runs from 0 to 2n minus 1. And we have x minus 1 f of x plus x times y. And what? So now we have two choices, two cases. When f is constant, what happens? This f of x is always 0 or 1. So you can just ignore there is nothing here, right? And if you see the coefficient in that case, x to the power of x times y, so it depends on y, right? So for each y, because it's just a coefficient for the ket y, but except for when y equals to 0, this all becomes 0. So it's obvious when y equals to 0, then its sum is 2 to the n, because when y is 0, this exponent is 0, so we are adding 1. How many times? 2 to the n. So we have 2 to the n. But if y is not 0, why is it 0? Why is the sum 0? Why is this sum 0?
The result becomes 0 if the y is equal to 0, because every base of y is 0, so the bit product will become, I think,
This is 0. So when y is 0, exponent is 0, so you're adding 1.
yes.
Okay. So that's okay. Why is this sum equals to 0 when y is not 0? Well, think of this naively. We have, if y not equals to 0 means that there is at least one place in the binary representation of y which is 1, right? So when there is 1, you can always make two pair of numbers, two sets of numbers. One set has the zeros on the ith place, and the other set has a 1 in the ith place. So you can split them up. you can split the sum into two summations. One has the sum of all the minus 1 to the power of x times y, where x has the 0 at the ith place, where y has the 1 at the ith place, and the other one has 1 at the ith place. So whatever you do here on the first sum, it will have a certain sign, let's say positive. And how about the other sum? Because the ith place has 1. The ith place of every number at the second sum is 1. It will be the opposite sign, right? It's the only difference between the first group. So there are many ways to think why this is 0. So let's say, suppose so there yi equals to 1. So then your sum, the entire sum, is split it into 2. So what I mean by this sum is it's the sum of all the numbers from 0 to 2 to the n minus 1, where ith place of that digit is 0, and this is the opposite. And compare these two. Everything else is the same, except that ith place is 0 here. So it will have certain sign because of this. It doesn't matter what x, y, I is, but we know what I is, but we will have some certain sign. But how about this? It will have another sign, right? So these two will have different signs. Whatever the value is, will have different signs. So it will be 0, right? So you can see another way why this is true. So think about the definition of our dot product. So you can rewrite this as the product of all the digits from 0 to n minus 1 of sum xi from 0 to 1 of minus 1 xi times yi, right? It's basically same idea of this one. So then you see this one, okay? So it's a sum, it's a product of something. So if any of this product factor is 0, then everything is 0. And suppose that you have yi equals to 1 for some I, right? So then what you're doing here is you're adding 1 when xi equals to 0 and minus 1 when xi equals to 1. So it's 1 minus 1, 0. So whenever you have yi equals to 1, this summation will become 0. So you're multiplying 0. So this is 0. Okay. So if it's constant, this happens. And what does it mean? This whole thing, if it's constant, this whole psi 3 is nothing but just the 0 ket, because every other ket state will have 0 coefficient. It means it vanishes, it doesn't exist. So, and the coefficient 2 to the n, so therefore this is simply this. So at the end of measurement, you always get 0. So so if you have 0, so far, you can guess maybe the function was constant, but it's not necessary. It's a sufficient condition. So let's see what happens when f is balanced. So f is balanced. What happens? Look at here. So balanced means that we're It's equal number of zeros and equal number of ones in the values of f whenever you plug in 2 to the n power of numbers. And I don't care what this state is going to be, but I just want to know if it's balanced, whether zero cat still exists or not. So let's see. My conclusion is there is no zero cat in this state. Why not? So let's suppose there is. So y equals to 0 means that we have minus 1 f of x, and since y equals to 0, all the coefficients is just this. And what is this? F is balanced. So there are equal number of zeros and ones. So there are equal number of minus ones and ones in the summation. So it's 0. Yes. So the coefficient of zero cat is 0. So I don't care about other states. Okay. So maybe some other state, they say 1 or 2, the base state 1 cat or 2 cat, may have 0 coefficient too, but I don't care about that. I just want to make sure that there cannot be 0 cat in the state when f is balanced. So that's enough, because if I see all the zeros in the measurement, then I know that it must be constant, because it cannot be balanced, because balanced case cannot give me the 0 cat. And on the other hand, if I see any one of measurement as 1, that means it cannot be constant. Therefore, it must be balanced, because the constant case have no other choice but we have cat 0. Okay. So you can definitely determine the characteristic of function by taking the measurement at the end of the quantum algorithm.
Professor, can this algorithm identify the third case, neither constant nor balanced?
So in the Dutch-Jozsa algorithm, so whenever you have a quantum algorithm, you need a circuit and you need a problem, computational problem. The Dutch-Jozsa problem assumes that function is always either constant or balanced.
How about the third case?
Well, we don't know. Yeah. So you're asking how do we find out the function when it's just randomly given?
Yes,
Well,
randomly given.
just check every input. There's no other way than just checking every input, right? If you want to find out the entire information of the function, that means you want to find out the input for every 2 to the power of n inputs, what the value of function is. Then you have to check every input and see what the value is. Yes?
By classical.
Yeah, but by classical way or whatever method, whatever the tool you have. Yeah. I mean, you see, if you want the complete information, there's no other way around, right? You want to know 10 of them, you just need to know, go through every single of 10, right? But you want to know something about this 10 thing, okay? But sometimes you don't need to go through all the 10s, like this one. If you just want to know about this information, then you can, but in a classical case too, you don't have to go through all the inputs here. At most, you can you can carry the function at most this much, but that's the worst case scenario, right? To find out the information. So, so you can reduce the computation, but this is the best we can do with the classical computer. But in the quantum computer or quantum algorithm, you can do it with one query, not even exponential. That's the catch. All right, so any questions? Okay, so let's look at another. So today we're gonna go through two more algorithms, and probably we can begin the quantum Fourier transform next time. All right, so next one is the Bernstein-Vazirani algorithm. So again, I should mention what the problem is. So the problem is we want to find out the function, what the function is, but we have a condition that we have a knowledge that this function is sending n-bit string to 1-bit string, and the rule of assignment is given by x to a dot x. Okay, so a dot x means that it's an inner product, just as we defined here. So a is also n-bit string, and x is also n-bit string. As long as, as far as we know what a is, we exactly know what f is. So the problem is, what is a? How do we find out what a is, given that we have function of this form? So in classical computer or classical situation, how many queries do we need to find out what a is? 2 to the n? We don't need that much. So again, so this is a n minus 1, x n minus 1, a0, x0. I need to know all the digits of a. What's the fastest way of doing this? So how do I do, what should I plug in for x if I want to find out what a0 is? Yes, 1, right? 0, 0, 0, 1, right? So if I want to find out a1 is, then 0, 0, 1, 0. So how many times do I need to do this? N, right? So, I cannot reduce less than n, right? So I need exactly n times of computing the function to find out what all the digits of a is. Now, the Bernstein-Vazirani algorithm is a quantum algorithm that can find the a with single query, with one query. So the situation is similar. The circuit is almost similar. So now I'm going to drop the tensor product superscript n because we know what it means. So you don't have to put the Hallmark here, but I just put it here. Doesn't matter. Anyway, so you can see that this is exactly the same type of the quantum circuit we saw before. This will do. So let's compute one by one. So I think we can just start from here, stage 1. So psi 1, 1 over n over 2, x from 0 to the n, x n, oh, sorry, it's 1 here. Okay, so 1, and then what? So psi 2 is, so only changes the output register. So 0 cat becomes fx cat, and 1 cat becomes fx minus 1 cat, right? I mean opposite here. And also, what do we know from here? So we have only the sign change of minus cat, right? And we know that this is a times a, so this is 2 to the n over 2, sum minus 1 a times x xn times minus cat. Okay, so let's do it again. Apply the Hadamard to get the third stage. So we have 2n over 2 x minus 1 a times x, and apply Hadamard here. We get y minus y times x, y, and so the entire xn becomes this large superposition again. And then apply Hadamard and minus 1 to get 1 cat. So that's why it doesn't really doesn't matter whether or not you applied Hadamard. So anyway, so I have another this coefficient. So we have 1 over 2 to the n and y and x minus 1, and let's combine these two, ax plus yx, and that's the coefficient of y. All right. So now we have same situation here, almost similar situation. You want to find out the value of each of the coefficient of each y cat. So look at this. Let's simplify this. We have x minus 1 a plus y times x. Okay. So by the way, even though I put the plus symbol here, I can replace it by O plus, which means binary addition, right? So I can replace it to binary addition because it all depends on the parity, not exact number. And also if I do that, then I know that I don't really need a plus symbol here, and it doesn't really mean anything when you put a plus symbol between binary number. It's a binary addition here. All right, so what this is going to be? Again, it's either 0 or non-zero, 0 or non-zero, which is 2 to the n. When does it become 0? Yes. If a plus y is not 0, then it must be 0. You see, if a plus y, let's say we replace it with z, then if z is not 0, means that there is at least one place which is 1. And you can separate the sum into one set with some certain symbol and the other set with exactly same value with the different symbol. So it all vanishes. And if a plus y equals to 0, then it's only case when you have everything. So in that case, everything is 0. So you're adding 1 because minus 1 to the power of 0 is 1. So you're adding 1 2 to the n times, so you get the 2 to the n, which is non-zero. Right? So it looks like a big sum, but what it really becomes is you have everything vanish except for y satisfying this equality. Right? So, oh, by the way, I mentioned, okay, so what is this a plus y means? I thought it was clear, but so a plus y, what does it mean? We have a is a(n minus 1, a0 as a binary representation, and y also as a binary representation. And when I say a plus y, these are not numbers. We're not adding two numbers, two integers. We're adding binary numbers by each places. So this is a(n minus 1 plus y(n minus 1), for that's the n minus 1 for place, and a0, y0. So that's what I mean. So it's another binary number, right? So again, what do we mean by it has zero? When does it become zero? What is y then? Yeah, huh? Y is? Well, y cannot be zero. Zero means that every digit of every place is zero. So, oh, yeah, y is equals to a. So one important assumption is that a cannot be zero. If a is zero, it's trivial, so we assume a is not zero. So in that case, only possible way that make this every digit equals to zero is that you have y, the digits of y exactly same as the digits of a at the same place, right? So y must be a. So what happens here? Your coefficient is 2 to the n, and every sum is just vanishes except for a, so we get a 1, right? Makes sense? Yeah. So what happens at the measurement? So when I take the measurement on input register, you have n measurement, basically. So every single qubit you measure is exactly the digits of A you want to find, right? So that's why it means that we can finish it with a single query. Any questions? So you see, it's getting stacking up in some sense. It's getting a little bit. So far, I'm not saying this is any way useful in real life, but we are getting there. So as you know, our goal is the Shor's algorithm, understanding the Shor's algorithm. And so far, every quantum algorithm we introduced is deterministic. We definitely know with 100% sure, as long as there is no error or measurement error or errors in the circuit, we definitely know what the information about of the function or oracle. And now, let's talk about different type of algorithm. So, in fact, quantum algorithm is most useful quantum algorithm is like this, and you will see a bit different from. You'll see you'll see this Simon's algorithm is a bit different from other algorithm we introduced. So here's our question. Now we are dealing with a function that sends n-bit string to n-1 bit string. So we have one less bit in the outputs from the input. And all we know is that if x plus y equals to a, which is not 0, so this is fixed, okay, then the value of function has to be the same. That's what we know. Okay. So that's why we're assuming that the output could be n-1 bit. Why? Because we can pair them up. We can pair all the 2 to the n power number of inputs into pairs, and we can assign different value for each pair, and that means that's the worst case scenario, right? So it doesn't mean that the function cannot be constant. Of course, function can be constant because it still satisfies this equality, this condition, right? But that's the easy case. So assuming the worst case scenario, that every pair of two inputs are assigned to different values, what is the minimum number of queries that you need to perform to ask to the function to find out what A is? We want to find out what A is here. So think about the worst case scenario. So if, I mean, think about the luckiest scenario, the best scenario. You pick two random points from this set, 2 to the n, and then luckily you got the same value of function, right? You got to evaluate the function and you got the same value. That means you can add these two inputs to get what a is, right? That's the luckiest situation, right? So in that case, you're done. But what's the worst? So you pick some number x1, okay? So you cannot do anything with just one. You pick another two, but the value of function x1 and f2 are different. So you don't know what a is yet. So you pick up another one, x3, and you computed the value here, but that's also different from the previous two. So what I mean by different is not just fx3 is different from xx2, it's also different from f of x1, okay? So you can keep doing it until when you finally get some xn whose value of function is somehow matches to the previous value you computed. Then now you find what a is, right? So suppose you've done this, so let's say m, for m inputs. So you want to find out all the combination of these numbers, pairs of combinations. So there are m choose 2 pairs we can make, right? So it's m minus 1 over 2. So if this is bigger than the total possibility of all the outputs, then there should be some pair which has the same value, right? You cannot have like more than this number of numbers to be assigned to each pair, right? So this is the number of pairs. M inputs, and this is the total number of. So you want to assign each pair of values. The values that you can assign is at most 2 to the n minus 1. So if it's bigger than, if the number of pairs is bigger than the number of value you can assign, then there must be some overlapping, right? So it's a pigeonhole problem, right? So if that happens, then, I mean, definitely you can find a. So roughly, if you see the approximation of m, then m is approximately 2 to the n over 2, right? I mean, not exactly, but so m squared is almost dominating m squared minus m, and it must be bigger than 2 to the n. So if your m is roughly around 2 to the n over 2, then you're gonna find out what a is. So you see, this is how much you have to compute in the worst case scenario, and mostly in average, you have to do this. And this grows exponentially as the size of problem increases. So n is the size of problem. So that's the best you can do. There's no other way. So what does Simon problem do? So Simon problem is trying to solve it in a more convenient way. So let me draw the circuit here. There's no H here. Okay. Again, it's so weird that there's nothing going on. It looks like there's nothing going on in the output register, and looks like the applying Hadamard twice on the input register should read as 0 after the measurement, but it does not. It does something. So let's start from 1 and compute up to 3. So what is psi 1? So we have 1 over 2 to the n over 2 x and just x and 0 n minus 1. Okay. And what is psi 2? So Oracle changes the output register f of x. Okay. And now what we're going to do is a little bit of thinking that even though I put f of x, this f of x, there will be 2 of them at least, right? The same f of x appears twice at least. So I'm going to pair them up. So if I say f of x equals to f of y, that means y plus x equals to a, and that also means that y is x plus a, right? So I'm gonna rewrite that as follows. So here the summation is running naively from 0 to 2 to the n minus 1, but here the running over the pairs x plus a with distinct x. Okay, just pick each pair and pick one of this element in the pair and then run the summation. That's what I mean. So x n plus x plus a n times f of x. Okay. So that's psi 2 and let's do psi 3. So we're applying a Hadamard on every case. So let's see, we have 1 over 2 to the n, x, and let's see, we have y minus x times y, yn, and y minus 1. So here x plus a times y n and f of x, right? Again, I'm going to rewrite this as follows. We have 1 over 2n y and summation over x. So again, the summation over x is not from 0 to 2 to the n minus 1. It's always runs for pairs. And we have minus 1 x times y, 1 plus. So you can also split this up as we did in the previous algorithm. X times y plus a times y. You can either plus o plus or just plus, doesn't matter. So anyway, we have common x times y term here. So we have a times y and y f of x n minus 1. Now let's see. So what happens? I mean, we don't know what this is. It's so complicated. So let's take a measurement. Let's assume that we took a measurement. So we got something, and what does it infer? So let me just take this coefficient and see when does this coefficient not become 0. So that's when we could measure the state y, right? So when does not become 0? When does not become 0? So in order to make this not equals to 0, I need at least this part, 1 plus minus 1 to the a plus a times y. not equals to 0, right? If this is 0, then everything is 0. So at least what I know after taking measurement is I know that a times y must be 0. Otherwise, it would be all 0 and should be observed after the measurement. So I know this, but I'm not saying that this is sufficient condition. It could be wrong. It could be another condition, but at least I know this, that my measurement outcome y has this, satisfies this equality here. So let me write down again. So Simon algorithm is not like just after taking one measurement, you get everything, every information. You need to do something more. So suppose that we take, let's say K, we run the circuit K times and obtained K measurement outcome. Let's say Y1. So let me write this way. So Y1 is Y1 n minus 1, Y1 0. So I need a double index, but I cannot put the subscript for the ith place, so I put the superscript here. So each Yij is going to be either 0 or 1, just the binary digits, a binary representation of Yi here, and up to Yk. Okay. So suppose that we got this. Okay, so all we know is that for each Yi, I know that the inner product with A, which is Y1 n minus 1, A n minus 1, up to Y1, 0, A 0 is 0. And same for Yk, Yk n minus 1, A n minus 1, Yk 0, A 0 equals to 0. So what do we have? We have system of equation, right? So if you're really unlucky, you can get the same equation twice, but let's not think about that right now. Let's say we just got this. We don't care about whether this is linearly dependent or linearly independent. And let's try to write it in the matrix form. So we have y1 n minus 1, y1 0, yk n minus 1, yk 0 times a0, a n minus 1, a0 here equals to 0. Okay. Oh, by the way, so every plus is O plus, not normal arithmetic plus. It's a binary addition. So we have this equation, matrix equation. We want to find out what A is. So how do we find out A in this case? How can we find? I mean, what's the necessary condition to find out exactly what AI is here? So let me give an example, because if we argue with this symbolic notation, maybe confusing. So let's say we have n equals to 3. So it means I have A2, A1, A0. And let me give you here. So we have 0, 1, 1, 1, 1, 0. So that's the simplest case here, but okay. We know what it is, right? Yeah, we know what this is. How about we don't have one of these? Oh, sorry, I should erase this part. How about this case?
Maybe the right people
Hmm?
two questions.
Okay, so here in the Simon's algorithm, we also assume that A is not equals to 0. So if A equals to 0, it's also trivial. So if A is not, suppose that A is not 0, can we determine A0, A1, A2? Yeah, of course, right? What is it?
A1 and A2 become 0 and
Yeah,
since it's at A1 A0 is.
we know what A0 is because we know A is not 0. So A0 must be 1, right? So how about 1, 1, 0, 0, 0, 1? What is A? Hmm? 1, 1, 0, yes. So we can find out what A is exactly with a unique one whenever we don't need entire 3 linearly independent vectors. How many? We only need 2. But we cannot know by 1, right? Suppose that we don't have this, then we know that A2 plus A1 equals to 0, but we don't know about A0, whether it's 0 or 1. So we cannot determine a unique A. So when we have this matrix equation to find out what A is, we need to know, at least n minus 1 linearly independent rows in this matrix. Right? So not n. We need n minus 1. We need this much. So the Simon algorithm is it's just try and error basically. It's not deterministic. We have to try. Like it's improbable, but you could have same vector or same y every time you take a measurement. Like in a infinitely low chance, but it's possible, right? It's not 0%. So in that case, you're never gonna find out what A is, but we're kind of assuming that there should be equal chances to get all the possible um, observations. So we get at the end, if we take the large number of measurement, let's say k is large, then we get n minus 1 linearly independent rows. So let's find out what actual probability would be. So the easy way to compute the probability of obtaining n minus 1 linearly independent rows is same as taking how many columns are linearly independent. So here's a theorem from linear algebra. So it's a rank theorem. So every matrix has the rank, row rank equals to column rank. What does that mean? So when you have a rows as a vectors to make a vector space, and you can take columns to make a vector space, they're called row vector space and column vector space respectively. And each vector space has a dimension, and the rank theorem says those two vector spaces have the same dimension. Okay? I'm not saying the ambient dimension. So the dimension of the row vector is n, and dimension of column vector is k. I'm not saying the dimension of vectors. I'm saying about the dimension of vector space. So if you have k number of rows in this matrix to be linearly independent, then you must have also k number of column vectors to be linearly independent. So that's the rank theorem. So even though we want the kn minus 1, we kind of, in this statement, we kind of meaning that we want at least my row rank to be n minus 1, but you can also say that we want the column rank of this matrix to be at least n minus 1. So the question is, what is the probability that the column rank is bigger than n minus 1? All right, so that's my question. And let's compute the probability that the first n minus 1 columns are linearly independent. So that's even smaller chance, right? Like if you have a first n minus 1 linearly independent columns is much lower chance than the entire column has at least n minus 1 linearly independent vectors. But let's compute the second one. So we first start from the leftmost. So it doesn't matter the index now. So I just need to know the columns here. Let's start from the left. You can start from the right if you want to. So let's start from the left column here. So if you need to get a linearly independent vector with the one single vector, all we need is that this vector must be non-zero. Okay? The first column vector. So again, the column vector, what's the dimension? It's k-dimensional. Must be non-zero. So what's the probability? So it's the complement of the probability when it's zero vector, right? What's the probability of having these as zero vector? It means that 0, 0, 1 out of all the possible choices, right? So there are 2 to the k possible choices of vector element. There's only one, which is 0, and we don't want that, so this is the probability. Okay. Now, let's go to the second. On the second column vector, the second column vector must be linearly independent to the first one. So what's the probability? Of course, it cannot be zero vector. Of course, it cannot be the first vector, right? What other choice can they have? I mean, what other things we have to exclude if you want the second column vector to be linearly independent to the first? I think that's it.
You should remove the case that the same as the first vector.
Yes, it cannot be same as the first vector, and also it cannot be the zero vector. There are only two cases that is linearly dependent to the first vector. So only two, we have to exclude two out of entire case. So this is the probability of second case. And you see the first and second are independent, right? You can, what's the technical, there's a technical term in the probability statistics that this incident is independent, right? So these two are independent of each other. So after all this, we're gonna just multiply these probabilities to get the entire probability. So how about the third? The third has to be linearly independent to the first and second. What's the probability? So you have two previous vectors, column vectors. You want the third vector to be linearly independent to the first two. So it cannot be any of the linear combination of first two, right? How many linear combination can you make out of two column vectors? So normally in the vector space or linear algebra, we deal with the real number. So whenever you talk about a linear combination, there are infinitely many. But here, we're not talking about the real numbers. We're talking about the binary digits. The numbers we have is 0 and 1. So all the linear combination you can get from two vectors is 4, right? So coefficient, there are two coefficients. There are two choices, 0 or 1 for each coefficient. So 2 times 2 is 4. So this is how much you get. This is the probability. So okay, so up to n minus 1 column, what do you get? So the probability that n minus 1 columns, the first are linearly independent is, so multiplying all the other, everything here. So 1 minus 1 over k, 1 minus 2 over 2k, up to 1 minus, so n minus 1. So n minus 2, 2k, right? Is this probability large or small? Do you think it's large or small? I think it depends on k, but it's pretty large. Let's see how large it is. So by arithmetic inequality, it's same as 1 minus 2 to the k minus 2 over 2 to the k minus up to 2n minus 2, 2 to the k. And let's take this out. So we have 2, 1 over 2 plus 1 over 4 plus, sorry, not 1 over 4. Right? Sorry, I should take this one out. So let's take 1 over 2 k minus n plus 1 here. So 1 over 2. So this part is 1 over 2 to the k minus n plus 1 times 1 over 2. So I'm going backward here. And 2 to the k, how can I make this? It's 1 over 2n minus 1, right? And how big n is, this is always less than 1. So this is 1 minus 1 over 2kn plus 1, right? So this probability is at least bigger than 1 minus this number. So let's say k is n plus x, something like that. So if I take a circuit, so k is the number of times I run the circuit, quantum circuit. And suppose that I run it x times more than the size of the problem. So x could be 10 or 20, not that much, okay? So then what this becomes is 1 minus 2 to the x plus 1. So if even x is 10, let's say x is 10 or 9, then it's 1 over 2 to the power of 10. So it's like 0.1%, right? So 1 minus 0.1% is 99.9%. So if you just try to find out if you just try to run the quantum circuit, the Simon's algorithm, 9 times more than the size of the problem, you get the answer. You will get the equation that enables you to find what A is with more than 99.9%. almost 100%, but not exactly 100%, but with a good chance. And if you fail, if you still didn't get the answer, and if you still get inefficient equation, then you can keep going on, right? And you will know that the probability will exponentially getting higher or getting closer to one every time you do it again and again. So you see, the mode of the quantum algorithm is getting a bit different from Simon's algorithm. So you're not getting a deterministic answer, but you get a chance, you get a probabilistic answer. But that probability, it's getting quite good. And how about the computational size, computational complexity? So in the beginning, the classical situation, if you want to find out the solution with the classical computer, then you need 2 to the n over 2 number of queries of the function. So that means exponential. The complexity is exponential. But in the quantum algorithm, it only grows linearly here. So it's kind of a trade-off. Like you get a linear complexity, but you're not going to get a deterministic answer. But fairly good, right? All right, so next time we're going to talk about quantum Fourier transform, and that's going to be much more fun, and it's going to be exciting. So see you on Wednesday.